Okay, so grade 10. Our next unit is relations and functions, page 389. This unit, yes, Sandy.
So let's say on the whatever criteria
A.
Like, so there's that little that counts like out of 4.
No, does not count.
Okay, so let's say we have I don't know, let's say our average is like 2.3, which is not my average. Would you average it to the 3 then?
Probably not, because I'm guessing if you got a 2.3, you only got 1 3. And most of your marks would be much lower.
Okay, no, like you have 2 3s.
If you have 2 3s, I'd average it to a 3. I'd probably average it to a 3. Because I also can do it with recent and consistent. There's a little bit of flexibility. So A, we're able to average or use recent and consistent. That's not consistent, though. That's a good thing, then. I am not going through each one of yours, like, situations.
The new report card going to count the polynomials test?
Yeah. Why would I be like, I'm not going to include this unit?
Because it was
like already on the first report card. At least
no, that's I see. Okay.
So I have a question. I got.
No, I'm not going.
5, 3,
no,
4,
no, no. I'm not. I'm not starting this game. Yes, Andy.
After this report card, marks like no, like after this report card,
I'll manage that.
Well, our next success would be like if I get like an 8 on my next test.
No, your marks do not disappear. But I mark on recent and consistent. And average criteria A for the most part. Okay. So our next unit is relations and functions. This unit's a lot of new information. So that's nice in some ways because it doesn't require a lot of like foundational skills from prior things. That being said, there's a lot of like, I would describe them as quirks to this unit and different pieces to remember. So it's not necessarily like conceptually hard to understand, but there's a lot of just pieces to it. It is harder than trig, is how I would describe it. The first, like today's lessons, super easy. I don't love how your workbook sets up this unit, so I'm going to kind of piecewise a few different things together. What do we call this grid thing? What's like the math term for the grid? Good, Cartesian plane. We all remember that. So within the Cartesian plane, there's some terminologies I want to review. We call this, let me write, this is quadrant 1 with Roman numerals. Then we have quadrant 2 is actually to the left, quadrant 3, and quadrant 4. It starts with quadrant 1 there because that's positive and positive for our x and y coordinates, right? It's our most often used quadrant. Why it goes counterclockwise, I think they just did that to annoy us as mathematicians. So we get a negative and then a positive, 2 negatives, and then a positive and negative when we're talking about our x and y coordinates. This is review from what, grade 6, maybe? We should remember this. Calling them quadrants 1, 2, 3, and 4, you should have learned before, but it's not something that's always like emphasized to you. I'm going to come back to page 390, but turn to page 392 now. I just don't love the order. So turn 2 pages to discrete and continuous data. So does anyone remember the difference between the two? Go ahead, Camille. Good, right on. So discrete would be unique data points. Write this down. Versus continuous is like a solid line. It has all of the decimals between the points. I'm going to say between the given points. it's continuous data, right? It has this fluid motion. So if I'm driving a vehicle and graphing my speed increasing, I'm consistently increasing up to 60, so I could draw a solid line. Versus if I was graphing the number of you in here that have a pet at home, that's going to be unique data or discrete data, so it would be separate data points. This is something that most cases, when I'd ask you to decide if something's discrete or continuous, it's going to be incredibly obvious, or I would give you a spot to explain your reasoning. I think your workbook actually does a very poor job of this, and some of the questions that they get you to label are up for a little bit of interpretation. So when I test you on this, it'll be very clearly one or the other. For the most part, a lot of our data is continuous. So they include some examples below. So time taken to complete a 100-meter sprint, that's going to be continuous data, because like your stopwatch, like when you click your stopwatch, it starts at 0, it goes through every possible second until you're done. The number of students who pass Math 10, that will be discrete data. Because you either passed or you didn't, there's no half a person. So the height of students, your workbook actually tells us this is continuous data. I would argue very strongly that this is discrete. I don't think there's going to be every possible height within the spectrum, right? Like from 5 foot to 6 feet, let's say, there's not going to be a person at every single height. There could be, but likely there isn't. So like if we were to do the height of everyone in this room, I'm not going to have continuous data. That being said, if I was to map like Carissa's height from birth to now, that's continuous because she's constantly growing, or she might plateau for a while and then grow, but it still would be consistent data.
So in order for something to be continuous, does it have to, the data points have to like relate to each other? Mm-hmm. So like if it was height of student, that would be discrete because discrete is people, is that right?
Yeah, that's a good way to put it. Just think of it. Shoe size, also discrete. Right? Like you either have a size 8 or size 9 kind of thing. Okay, so now let's turn back just like one page to page 390. So this is, like this question is going to be a large portion of this unit and doing questions like this. This unit, we could do a lot of criteria C assignments because we're talking about relating two things together. So, and graphing it. If I can graph something, I can make a data table. Often, if I can make a data table, I also can make an equation to represent it. All of the different forms of representation. So the example they have here is we're going to use toothpicks to form a triangle. So on my first triangle, how many toothpicks would be in that one? 3. Second triangle, though, how many toothpicks are there? Sorry, when there's 2 triangles, how many toothpicks? 5. So I only had to add 2 more. So when there's 3 triangles, how many toothpicks are there now? 7. Again, I only had to add 2 more, right? Because my additional 2 triangles, or my additional triangle uses a triangle aside from the previous ones. So the first question says, draw the next 2 diagrams in the pattern. So that would be my current 3 triangles. If I add 2 more toothpicks, there would be my 4. I'm going to use that same like colors. 1, 2, 3, 4, and then I can add 2 more toothpicks, and I get my 5 triangles. So I can put this data into a pretty little data table. Number of triangles, they've labeled with a capital T. Number of toothpicks, they've also labeled with a capital T. Capitalization matters. So they've used capitals here, so we need to use capitals. They use lowercase, use lowercase. So one triangle, it was 3. We're just going to fill in these numbers. So that was 5, 7, 9, and 11. This is a linear relation. So they have that title there at the top. For something to be linear, it's going to have a constant rate of change. we will come across things in this unit that are linear, but we'll also come across things that have exponential growth, or they have like an exponent involved with them. When I ask you to graph something or to come up with the equation, for the most part, they will be linear, or very simple, like it's x squared, like a very simple exponent with it. It won't get super complicated with exponents. So this one, the constant rate of change is that it's +2 each time. Why is this discrete data? But why is it a specific number? Relate it back to the concept. We're talking about toothpicks. So each time we're only ever, good, we're only adding whole toothpicks, right? I'm not adding like a broken toothpick here. So on questions like this, when they ask like why it doesn't, go back to like, usually there's going to be a concept here or like a situation. Your reasoning should match the situation. So this is discrete data because we're talking in whole toothpicks. Yes, I know we could break those toothpicks, but in order to form a triangle, I need a whole toothpick there, right? So it's coming back to that situation. Looking at our data table here, could you guys describe a relationship between the triangles and the toothpicks? Good, right on. So double, you could describe this a few different ways. If we double the number of triangles, and add 1, it's going to equal our number of toothpicks. I could write this as an equation then, as P is going to equal 2 toothpicks plus 1. As this unit goes on and we get into like the second half of this unit, which is more of just linear relations, we'll go through really how to calculate and not just have to use number sense to figure out that equation. Okay, let's graph this. So T, so my number of triangles is at the bottom. So I have 1, 2, 3, 4, 5, 6 triangles. And then our number of toothpicks is going vertically. You can go up by 2s here. Like really I'm going up by 1s, but I'm only going to label every other one, just so I don't have to write everything down. That's totally fine. So then we're going to fill in our blank. So 1, we had 3, 2 is 5, 3 is 7, 4 is 9, and 5 would be 11. My dots form a nice straight line. Each time I could go up 2 and over 1. Up 2 over 1. So there's that consistent kind of change there to help to make sure you wrote it out correctly. This next portion should be review from grade 8. So using our equation to determine the number of toothpicks if there's 27 triangles. How do I figure that out? It says using the equation. You have to actually show yourself plugging it into your equation. Where do I put the 27? Good, I'm going to substitute with the t. So I can write 2 times 27 plus 1. So 2 times 27 gives us 54, which is 55. You very much could go straight to 55. That's pretty easy math. That's fine if you don't want to show it. Next question says, use the equation to determine the number of triangles if there's 83 toothpicks. So where's that 83 go then? Good. Sorry, no, 83 toothpicks. Toothpicks was P.
Oh, okay.
So it's good. So instead of writing P, I'm going to replace it with the 83. And now I have to work backwards. How do I solve for the T? What's the first portion I can cancel out? Good. So we have to cancel out our constant. So I get 82 equals 2T. How do I get rid of the 2? Divide. So 41, that's a terrible 4. 41 triangles. No, because it specifically says use the equation. As well, like this one's pretty simple. I would suggest using your equation because it's always going to be, it's likely going to be a little bit harder. Okay, that's lesson 1. I'm not going to give you any practice questions from lesson 1. It's a pretty straightforward lesson. Turn to page 399. So that's lesson 2 we're going to cover. So a lot of this unit is terminology, and that's what most of this portion of this lesson is. It's like terms you might have heard before and some new ones. It's not super difficult. In math, so if you have your workbooks, I would highlight this. A comparison between 2 sets of elements is a relation. We say elements, it's like the math term for things. So relationship, a comparison between 2 things is a relation. So comparing X and Y, comparing number of students compared to heights, comparing number of students to number of pets, like any comparison is a relation. That's how you can say it fancier using math language. Within this unit, we're going to talk a lot about different ways we can represent relations. So you already know we could represent them in words, with a data table, with ordered pairs, an equation, and a graph. Our new ones that you're going to learn are a mapping or an arrow diagram. I usually call them arrow diagrams, and function notation. Function notation is like the second half of this unit. Today we're going to learn about arrow diagrams. Arrow diagrams, in my opinion, are incredibly useless. And like you're going to see them in grade 10 and never again. They're a thing, they do exist, but they're just not that helpful. So they're going through a scenario. So if I'm comparing the cost of driving compared to the speed, there's a relationship there, right? A lot of vehicles now, like any somewhat newer vehicle, shows your fuel economy. Have you heard your parents talk about your fuel economy? Yeah, some parents get really into it, some parents not so much. But there's like a sweet spot when you're driving, and it depends on the vehicle to get your best mileage or the best like cost per kilometer. Usually it's like highway driving is your best. Usually it costs more for you to drive like in the city where you're stopping and starting more versus on the highway where you can go like 115 pretty consistently. That's usually your sweet spot. So this next bit is a comparison here. Very specifically, they have labeled our variables with a capital C for cost and a lowercase s for speed. You need to then be consistent with using a capital C and a lowercase s. Within that, C is our dependent variable. And that's because the cost of driving would depend on our speed. S, therefore, is our independent variable. Our independent variable we might also call the input. Dependent variable is our output. We're going to make a little summary chart. Inputs make up our domain, and our outputs make up our range. So they have presented all of these new terms for us, I think, in a very complicated way. So let's make a little table and summarize this. Really, we're talking about different ways we can define X and Y. So if I'm talking about X and Y, X we would describe as our independent variable. Versus Y is your dependent. Just like right now, your parents are independent people, you are very much depend on your parents. X is also referred to as your input. Y is your output. Another way you can describe your X values is your domain. And Y is your range. So X would be like our horizontal, y is your vertical, like on your graphs. That terminology is really important. That terminology, we'll use that terminology like in questions, and I'll be like, describe the domain here. You have to know what domain means. That's going to come up a lot more in tomorrow's class. But that language is like expectation that you're going to know. We're going to go through it's a lot more, so it'll make a little bit more sense. But questions will be vague and use these, and you have to interpret them correctly. So just remember, whenever it says independent, it's talking about your x variable. Okay, so if you turn the page, they give us an example here, continuing on with this whole speed and cost analogy. So they're saying here, S, my input or my speed would be our better title compared to my cost. Notice here, when we go 20 kilometers an hour, it's going to cost us, I forget, cents per kilometer. So 10 cents per kilometer, it's going to cost us. It's also going to cost us that same amount if you go 120. So your cost is high, it gets lower and lower and lower, and then it increases again, forming this shape here. Does anyone know what we call this U shape? No. So that shape is called a parabola. Spelt parabola, but we say parabola. That's the name for the U shape. A parabola is always symmetrical. So like the angles of the U are symmetrical, but it could be a wider U, it could be a steeper U, it can be an upside down U. Like the orientation of the U can change quite a bit, but it's symmetrical. We have ordered pairs. That shouldn't be anything new there. Then we have this mapping diagram or the arrow diagram. So a few comments about that. We will do our next criteria CD assignment. You're going to have to do these things. So this is really important here. So you need to title your two ovals. It should always be your X to your Y. And then you don't repeat numbers. So specifically, like that 10 was in my data table twice, but they just drew like the two arrows both going to the same 10. Okay, your numbers should also be listed. Smallest to largest. Do you guys see though, like looking at these four forms of representation, that mapping diagram, not super helpful. And that's why it's not used a lot. It does exist in certain cases, it could be helpful, but like overall not incredibly helpful. Go ahead. Yeah. Yeah. It's in the curriculum, I have to make sure you know it. That being said, like it will not be emphasized. There are much more important things than those. The next page is a continuation of the same problem. They've now given an equation to represent it. So they've said, I'm just not going to scroll there, so you guys are still copying down. But they've represented this scenario with an equation. Next year in grade 11, we will teach you how to come up with that equation. This equation, like it's a gross equation, 0.001 s squared minus, like it's not a pretty equation, but next year you'll learn how to develop that equation. Your graphing calculator does most of the work. But that's like the equation to represent it. I would never expect you to come up with it in grade 10. Okay, turn the page again. So this is page 402. This is a little summary again of kind of everything we've done, written out in another just like format. So if you have the equation y equals 3x minus 5, our x is our independent variable, which is our input, which is our horizontal axis, your first coordinate. The one that they're missing is it represents your domain.
So your x values, your potential x values here, it's just an equation, so my domain could be anything, right? Because I could plug in any number my heart desires for x. But if there was context to it, so like back to our speed, I can't have a negative speed. You can because you're decelerating, but like in their context, it's just speeding up, right? So that's your domain. Your dependent variable is your y, which is your output. Our second coordinate, our vertical axis, also called what? Do you guys remember? Range. So later on this week and next week, we're going to use your graphing calculators a lot. You need to be bringing them to class. Domain and range is what's used, like the terminology within your graphing calculator. Do we all have graphing calculators at this point? Okay, you don't need it today. Bring it with you for our next couple classes. Turn the page. So here they've given us an example here of data represented different ways. So they said state the independent variable for each one of these. I'm just going to highlight to color coordinate them. So our independent variable comes back to our x values. So in this first example, 5, 8, 11, specifically the p would be our independent variables. In example 2, your first column in any data table should be your x, or your independent variables again. And the last example, your first coordinate is always your independent variable. Your dependent variable is like the flip side, the remainders, or the second like half of it. So just pretty much terminology of things we kind of already know. Okay, turn to page 405. So here we're going to go through all of this, connecting the different things together on an example. This is like a very kind of standard question for this unit. We will continue adding more questions to one like this. These questions take a long time. So consider the relationship described by the equation y equals x squared minus 6. So first step, let's complete that data table. So we're given our inputs, and then they want us to find our outputs. In order to find our output, all we're going to do is plug it into that equation. You could probably do this in your head. I'm going to write it out. But if you can do it in your head, that's just fine by me. So when you fill it in, be very careful. Treat your x values, like our inputs that we're plugging in, like they're in brackets. So I would do 4 squared, which is 16 minus 6, gives us 10. 3 squared, 9, minus 6 is 3. I will not on your test ask you to ever list out your ordered pairs like this. I really feel like you guys all can do that by now. 2 squared minus 6, so that's 4 minus 6 gives us negative 2. 1 squared is 1. 1 minus 6 gives us negative 5. Zero squared is 0, so 0 minus 6 is negative 6. I just want to pause here for a second. So I said earlier, for it to be a linear graph, it has to have a constant rate of change. Notice on this one, my difference between the first two was 7. Then my difference was 5. Then my difference was 7. Then my difference was 1. Is that constant? No, so my shape is not going to be a straight line. That's kind of like a hint for you. At this point, this one's also going to be a parabola. I don't expect you to have that like known. You should just be recognizing I'm not getting a straight line here. Go ahead.
Why did you put brackets around the 2?
1, 3. I just didn't write it around the 0. That's my fault.
Or like, why do you put brackets around
You
2?
don't need them on the first ones, but we do need them when we get to the negatives. So I'm just trying to emphasize it for you. So the reason why right now, like when I plug in -1, -1 times -1 gives me a +1. If you don't have brackets, it's still going to be a negative. So now +1 minus 6 gives me -5. And so I'm just trying to emphasize that for you. Truthfully, for the first ones, you don't need the brackets because they are positives. But now you should have them. So now when I plug in -2, I'm going to get a +4 minus 6 gives me -2. So you can see my y values are repeating themselves now. That's a really good question, Camden. So then I get 9 minus 6, which gives me 3. -4 gives me 16. 16 minus 6 gives me 10 again. So because of that squared and how it interacts with the negative, that's where we get this parabola shape. So a couple comments, we're going to graph this. Your workbook has tried to like darken the lines for you. Sometimes they do a really good job of it and sometimes they don't. I always try to redraw like the axes lines just because I find it's helpful that you don't mess up to record them again, like when you're plotting your points. Also, the numbers when they're printed sometimes get printed a little bit off. So just be careful where like that you're darkening the correct line for your, like in this case, they did 5s. Just to be careful when you're actually plotting, sometimes it's kind of wonky. Okay, so when we plot this, I recommend starting at a couple key points. So plotting our 0 and -6, I find really helpful as it's my kind of center point there. We call that point our y-intercept. We're going to talk about more about that tomorrow, but it's where it literally crosses our y-axis. It intercepts that y-axis. Our x-intercepts are at decimal points, so they exist, but we don't have them in our data tables. So from here, at -1 for x, it goes to -5. So here I have a point. I also have a point at that like mirrored point at +1 and -5. At 2, we get 2. Sorry, -2 and -2. So same idea. +2, I get -2. -3, I get 3. So it's just a little bit easier to find like a pattern I find when you're plotting the points. Totally personal preference. So at 4, we get 10. I can connect these points because I could have plugged in any number for x. If I plugged in a decimal for x, I'm going to get a decimal. Where it crosses your x-axis, we call our x-intercept. We call this shape a parabola. Because it's not a straight line. I've like said some of these answers, I'm not filling them all in though. As we go on through this unit, we will start graphing this with your calculators. So that way you wouldn't actually have to plot all these points. And then you will answer questions from using your graphing calculator. Part of this unit, using your graphing calculator, like I have to teach you what buttons to press. So like when it comes to your test, you can't ask me questions on how to use your calculator. I will go through it in a lot of detail, but it's like an expectation that you know how to use your graphing calculators, which makes it that much more important that you're bringing them to class, because a lot of the things you do in your calculator aren't like intuitive sequences of buttons to press. Okay, so we have 20 minutes left in class. That's the last thing I'm going to cover. You only have to do in lesson 2 numbers 5 and 6, which are like 2 more questions similar to that one we just did. You don't have to do anything from lesson 1. So you're aware, in case you get sick or you have to go in quarantine or work from home, I've posted, just like last time, that same like Google Doc type file that will have everything for you. So like all of our assigned questions, I will post all the videos and stuff here for you as well. Kind of just like we've been doing in the past. Yeah, numbers 5 and 6, that's it.